In the name of Almighty God, I'm Master Sankosha, and today I want to talk about multibody dynamics theory. This chapter introduces you to the theory, which is specific for the multibody dynamics interface features. In this chapter, we wanna go to joint theory, camp follower theory, gear pair theory, rigid body contact theory. Now I want to go through the first sections, joint theory. In these sections, we want to go through representation of rotations, prismatic joint theory, hinge joint theory, cylindrical joint theory, screw joint theory, planar joint theory, ball joint theory, slot joint theory, reduced slot joint theory, clearance joint theory, fixed joint theory, distance joint theory. Universal joint theory, theory for joint constraint, theory for joint locking, theory for springs and dampers on joints, theory for prescribed motion on joints, theory for applied forces and moments on joints, theory for friction in joints, theory for joint forces and moments computation. Now I want to go through the first chapter, representation of rotations. In two dimensions models, the rotations can only occur around the z-axis. It is represented by a scalar angle theta. In three dimensions, the situation is more complex. There are three rotational degrees of freedom. For infinite rotations, however, any choice of three rotation parameters is singular at some specific set of angles. For this reason, a four-parameter quaternion representation is used for the rotations in the joints. The quaternion parameters are called A, B, C, D, and D. These parameters are not independent, so an extra equation stating that the following rotation relation is added, such as a to the power of 2 plus b to the power of 2 plus c to the power of 2 plus d to the power of 2 is equal to 1. The four quaternion parameters are often represented as one scalar and one vector. The connection between the quaternion parameters and rotation matrix R is such as these matrices. The rotation can also be represented as a rotation vector with direction E and a magnitude theta. The magnitude of the rotation is such as theta is equal to 2 arc cosinus alpha, and the direction is theta is equal to b divided by absolute b. The parameter R can thus be considered as meaning and measuring the rotation, while B, C, and D can be interpreted as the orientation of the rotation vector. For small rotations, the relation simplifies to these matrices. Successive rotations are represented by quaternion multiplications, just as finite rotations, quaternion multiplications are not commutative. Prismatic joint theory. The prismatic joint, also known as translational or sliding joint, has one translational degree of freedom between the two connected components. The components are free to translate or slide relative to each other along the joint axis and its local coordinate system. The local coordinate system of a joint, which can be seen as rigidly connected to the source attachment, consists of three axes: joint axis, second axis, and third axis. You specify the initial direction joint axis using one of the following methods: method 1, 2, 3. Method 1, give the components explicitly in a selected coordinate system. Select one of the axes of a selected coordinate system. Method 3 is select an edge that is parallel to the joint axis. For all methods, the axis is normalized to give a unit vector. In method 3, the direction that has a positive projection on a global x-axis is selected. If the projection of the x-axis is very small, the edge is almost perpendicular to the x-axis. Then the y-axis is used in the projection criterion. If the edge is perpendicular also to the y-axis, the z-axis is used as the joint axis. You can also choose to reverse the direction of initial joint axis if the directions of the second and third axis are important. For example, when interpreting to joint force results in the joint local coordinate system, or when there is elasticity in the joint, then the method 2 is preferred because this gives full control over all three axes. When an axis in the selected coordinate system is chosen to specify the joint axis, the other two axes are determined through cyclic permutation. For method 2 and 3, the initial second axis and initial third axis are computed internally as described below. The initial second axis E20 perpendicular to the initial joint axis is computed by making an auxiliary axis, an axis not parallel to the initial joint axis, and then taking a cross product of the initial joint axis. In this auxiliary axis, the initial third axis is computed by taking a cross product of the initial joint axis and the initial second axis. E30 is equal to E10 multiplied by E20. Finally, the rotated axis in the deformed configuration are formed by rotation the individual axis using the rotation matrix of the source attachment. For two-dimensional models, the generation of the coordinate system is significantly simplified. The initial third axis is taken as the out-of-plane axis. The initial second axis E20 is orthogonal to E10 and E13. The next type could be prismatic joint formulation. For a prismatic joint, the destination attachment is free to translate relative to the source attachment along the joint axis. The added degree of freedom is thus the relative displacement along the joint axis. The translational motion of the source and destination attachments at the center of the joint can be computed as these equations, where for the source and destination attachment respectively, we have a UC, CSCRC, and UC destination are the displacement vectors for the attachment at the center of the joint. Our source and our destination as are the rotation matrices describing the rotation of attachment, and XC source and destination are the positions of the centroid of attachments, and US source destination are the displacement at the centroid of the attachment, and XC is the joint center. To formulate this kind of connection for a rigid joint, the motion of the destination attachment is prescribed in terms of motion of the source attachment. The displacement vector and the quaternion vector for the source and destination attachments are defined as follows. The relative displacement vector in the global spatial coordinate system is defined as follows. For two dimensions, the motion of the destination attachment is prescribed in terms of the motion of source attachment as follows, where phi is the rotation about the z-axis out of plane axis. Now I want to go through the next sections. Joint elasticity in prismatic joint. In the case that the joint is elastic and the elastic displacements and the rotations are added to the source motion, so that the displacement and rotations at the center of joint is no longer equal for the source and destination attachment as follows. The elastic translation and rotation vectors are expressed in terms of the joint axis as follows. Here U2, U3, theta 1, theta 2, theta 3 are the default elastic degrees of freedom available for the subjoint. Optionally, only a subset of them can be chosen to be elastic. The quaternion representing the elastic rotation is as follows, and then can be computed from the elastic rotation vector theta EL. The spring and damping forces and moments are proportional to the elastic displacement and velocities. The spring and damping matrices are subdivided into four parts depending on whether they relate to translation or rotation. The matrices which couple translation and rotations are optional in the input data. The total elastic joint forces and moments can be written using the spring and damping forces and moments as follows. The contribution to the virtual work is delta W is equal to FAEL multiplied by delta UAEL plus MEL multiplied by delta EL. Thank you so much for watching my tutorial video until the end. Today is the 7th day of June 2026. Time is 6:09 in the morning. Also, you can download the proven and appropriate Computer Mathematics Simulation file from github.com/master's.